Calcutta. I know Professor Ghosh, or Anila as I call him, for a very long time. And to give us a little background on him, so he did his PhD from ISI Calcutta in 2004 under obviously the supervision of Professor Prabal Chaudhary, whom you heard. So we are academic brothers, by the way. And he is now a full professor at ISI Calcutta, and he is a very well-known statistician in India and abroad. And this year, he was awarded with the prestigious C.R. Rao prize for his contribution to his districts. So he will talk about distance-based statistical methods for high-dimensional data, and I would like all of us to welcome him.
Thank you, Anubhav. Thanks for kind words and also for inviting me to this workshop. So, as Radha suggests, I will be speaking on distance-based statistical methods for high-dimensional data. So, what do you mean by high-dimensional data? Here are some examples. So, for example, this is lymphoma dataset, which contains microarray gene expression levels for 4,026 genes for 42 diffuse large B cell lymphoma, 9 follicular lymphoma, and 11 say CLL samples. So, basically, what we have here is a sample of size 42 plus 9 plus 11. That means 62 observations from 3 classes, and on the other hand, each of the observation is of dimension 4026. Okay, so we are in the era of high dimension, low sample size data. So the data set is of much higher dimension compared to sample size. So we will be dealing with mainly this type of data set to do some statistical analysis. For instance, here I have 3 classes, and from these 3 classes I have some observations in 42, 9 and 11 observations, and I have each observation of dimension 4026. Suppose that I want to develop a classification rule. That means a new if gene expression level of new cell is given to me, then I have to judge whether it is coming from which of the DLBCL or FL or CLL classes. That means I need to develop a classifier. And you know that the standard methods like Fisher's discriminant analysis, which is called linear discriminant analysis, cannot be used in this case. Why? Because it involves inversion of the sample dispersion matrix. And in such cases, the sample dispersion matrix will become singular and we cannot invert it. And not only for classification, in various other cases, like in the case of 2 sample testing, you know the Hotelling T-square is one of the methods to test whether the 2 distributions are identical or not. But Hotelling T-square also involves an inversion of the sample dispersion matrix, which we cannot do in such cases. So those statistical methods cannot be used in such high dimensional low sample size setup. So here are a few other examples. I am skipping all of this. Those are not important for me. So let me just remind you that I will be dealing with the data sets where the number of features are much more as compared to the sample size. So as I have mentioned, so there are some problems with the traditional methods. For instance, what about parametric methods? In the case of parametric methods, what do? We assume some parametric model assumption about the underlying distribution, and after that estimate the parameters. So first of all, it is very difficult to judge the validity of the model assumptions in high dimension. Right? In the parametric setup, what do? You assume some parametric model for the underlying population, and after that you do something based on that. Basically, you estimate the parameters. Now, in parametric method, it will work well when the model assumptions are correct. If the model assumptions are erroneous, then it will lead to anywhere. So first of all, one needs to check whether the model assumption that you have made is correct or not. And for that, one needs to check the validity of the model assumption. In 1 dimension or 2 dimension, we know we can use the frequency chi-square test to do that. But in higher dimension, you must have seen that there is no frequency chi-square test for that. Goodness of you. Because a frequency chi-square test is a large sample test. In order to use it reasonably, you have to have reasonable samples in each of these cells. But if you have too many variables, then the number of cells grows up exponentially and most of the cells will be empty. Okay? So it is difficult to check the validity of the model assumption. And even if the model assumption is correct, for instance, if I know two distributions that I am dealing with a normal, they have also holding t-square, I cannot use because of the fact that I have said that the sample dispersion matrix is not inversible. On the other hand, non-parametric methods, we know that compared to the parametric method, to get a reasonable result with the non-parametric method, we need to have more sample size. So when we have less sample size, it is very difficult to use a non-parametric method meaningfully. The standard non-parametric method, because the cost of dimensionality kicks in. Okay, and on the top of that, the computing cost for some of the non-parametric methods also grows up exponentially as the dimension increases. So this is the problem that we face in the case of analyzing high-dimensional low sample size data. Parametric method, difficult to check model assumption. Even if I assume that the model assumptions are correct, then also I have some problem in using the traditional methods. On the other hand, non-parametric methods, they are more flexible. We do not need to have any parametric model assumptions. But we have the big problem of Course of dimensionality, and on the top of that, the computational cost may go high. So what do we need here? So here we need to construct some non-parametric methods which can be meaningfully used in high-dimensional low sample size setup, and not only that, it should be computationally tractable. Okay? So in this talk, I will be mainly considering some distance-based methods. There are several ways of dealing that. Not only that you have to use distance-based methods. There are several ways to do that. But in this talk, I will be mainly concentrating on distance-based method. Though I have written it in this way, we will mainly consider two different problems. One is the two-sample test, another is supervised and unsupervised classification. But I don't think I will be able to cover the second one, so I will mainly concentrate on the two-sample test. Okay? And as we go on, we will describe several methods and study their high-dimensional behavior to understand what is going on. Okay. So let's start with the setup of two-sample testing. So I have observations. I have observations. I have observations from two different populations. F denotes one population and G is another. So I have some observation from the first distribution, that is F. I have some observation from the other distribution, G. I want to test whether the two distributions are identical or not. Okay. So this is the problem. Okay, fine. So here is one example, one Arsine data set that was on the first slide, which contains 10,000 dimensional observations from two classes. There are 390 observations from one class and 502 from the second class. So basically, here M is the sample size from the first class, that is 398. N is the sample size from the second class, that is 502. And our D is much bigger than. Okay. So as I have mentioned, here for this problem, I'll be discussing some methods based on pairwise distances because the traditional methods have some problem. So you may ask me, why pairwise distance? First of all, it is computationally easier. You can compute it for data of any arbitrary dimension. And on the top of that, we have a nice property. This is a result due to Ma, Paul, Bartolomewski. They said that x1 and x2 are the observations from this class F, y1 and y2 are the observations from this class G. So I am considering four independent observations, x1, x2, y1, y2, two from the first class, two from the second class. The result says that the distribution of this norm, and the distribution of this, one from the first class, one from the second class, and here we have both from the second class. The distribution of these three things are identical if and only if f and g are identical. So if the distributions f and g differ, that distribution will also differ. So that means pairwise Euclidean distances contain some information about the separability between the two populations, and we will be trying to extract that. Okay? So this is one motivation of using pairwise distances, and we will be using simple pairwise Euclidean distances, and later in the later part of the talk, instead of Euclidean distance, we will be going for some other distances. But after all, we will be using pairwise distances to construct some meaningful tests. So let us look at the literature. What are the tests that we have? So here is one famous graph-based test by Friedman and Lasky. It is known as a multivariate run test. I have written MST run test because we will be using MST for its construction. So it is one multivariate run test that we have in the literature. What is run test? That we know in the one-dimensional setup, right? We have some observations from A, some observation from G in one dimension. You can arrange the observation in increasing order, and after that you can count the number of runs, right? So suppose I have some one-dimensional observation. So cross represents observation from one class, and 0 represents observation from other class. Suppose I have arranged the observation and I got a sequence like this. Okay, so what is run? So this is run means a sequence of same symbol. So here this is one run, this is another, this is another, this is another, this is another. Here we have another run. And so number of runs turns out to 1, 2, 3, 4, 5, 6, 7. So we can count the number of runs and construct a test based on that in the univariate setup. So if the two distributions are identical, that means f and g have no difference, then what do we expect? The observations are mixed up, so we expect the number of runs to be higher. And if the one distribution is completely separated from the other one, then all process will be followed by a sequence of circles, right? The number of runs will be 2 or very small. So if the number of runs is small, we can reject the null hypothesis, that is f equal to g, and say that the two distributions differ significantly. So that is in one-dimensional set. What about higher dimension? How can I define multivariate run test for higher dimensional problem? One major difficulty is that in the multivariate case we do not have any natural ordering. Okay? So the simple straightforward extension of this multivariate run test is not possible. So Friedman came up with a nice idea. What was his idea? So here Z is a combined sample. Okay. So first n observations are from the first class and the next n are from the second class. So it defines, so we have a set of m plus n observation which is denoted by Zn. It's a collection of m plus n observations. Right? So here. So m of them are from the first class and the next n are from the second class. Now I am considering a graph. Graph means it will have some vertices. Suppose that these are two-dimensional observations. So if these are two-dimensional observations, collection of two-dimensional observations, suppose that here I can plot it, here x and y, the other way around. So this is one observation, because this is another observation, this is another observation, and so on. Okay, this is a collection of n plus n observations. Now I am considering a complete graph. Complete graph means between any pair of vertices there is an edge. Okay, so this one is connected to all other vertices. Similarly, this one is connected to all other vertices, and so on. So I have a complete graph like this. And here you have several other things. It's a complete graph. And in the complete graph, each of these edges has a weight or a cost associated with it. What is the edge weight? It is, suppose this is the first vertex Z1, this is the second vertex Z2. Now this is the edge. Now I am attaching a weight to this edge. The weight is same as the Euclidean distance. Okay? So I have m plus n observation. Now I am considering a graph where the vertex, each vertex represents one observation. I am considering a complete graph where any two vertices are connected. And the edge connecting Z1 and Z2 or Zi and Zj has weight same as the Euclidean distance between these two observations. Okay? So starting with this complete graph, and after that, from this complete graph, I am trying to find the minimal spanning tree. Do you have an idea what is minimal spanning tree? You have an idea? Okay. Anyone who doesn't have any idea? Okay, fine. So this graph is connected, right? If I remove this edge, it will still become connected. Connected means starting from here, these are the paths. Following these paths, I can go anywhere. Right? There should be a path starting from Z1 to say Z4. There is path. There is a path, right? So connected means starting from a vertex, you can always reach another vertex following a path. Then it is connected. So for instance, suppose here I have 4 vertices. So this is a connected graph. Because starting from here, you can reach here by this route. You can reach here by this route. Okay? But if this is the case, then this is not connected because starting from here, you cannot reach here. So suppose, so now here, suppose that, okay, forget it. Suppose that a graph has 5 vertices. Okay? I want a connected graph on 5 vertices. How many edges do I need to take? 4, right? 4 is the minimum number of edges that I need to take. So here, in order to make it connected, I need to consider n plus n minus 1 such edges. Okay? So I'll be choosing the edges in such a way, okay, so each of these n plus n minus 1 edges has a cost associated with it. So these are like n plus n cities in a country. And I want to connect each of the cities by a common road map. Now, for constructing those roads, I have a cost associated with it, which is basically equivalent to the distance. Okay? So you can, this choice of n plus n minus 1 many vertices, which will make the graph connected, is not unique. You can choose it some other way, I can choose it some other way. Right? Now you have given me one choice. For that choice, there is an associated cost. For my choice, there will be another associated cost. So for each of these n plus n minus 1 many edges, which will make the graph connected, there is an associated cost. Okay? I am trying to find those n plus 1 those n plus n minus 1 many edges for which the total cost will be minimum. Okay? And that is known as the minimal spanning tree. As a tree, it doesn't have any cycle. That means starting from here. So if this is the graph, then it is a cycle. Starting from here, without repeating its path, you can come back here. So this type of graph is not going to contain any cycle. This is called tree. This is a spanning tree because it connects all the edges. And minimum because the cost is minimum. Okay. So what Friedman did, he considered the minimal spanning tree on the set of n plus n minus n 1 many vertices. So suppose these are my observations from the first class and these are my observations from the second class. Okay. So I have a complete graph on this many vertices, and from that complete graph I will be choosing those n plus n minus 1 many vertices to get minimal spanning tree. Suppose this is the minimal spanning tree that I have. Okay, this is smaller, so it could be like this. So suppose this is the minimal spanning tree. So what he suggested, after constructing this minimal spanning tree, you look at the edges which connect observations from two different classes. Like here, I have an edge connecting observation, one observation from F and one observation from G. Now I will remove this edge. Okay? So this edge will be removed. I have another edge of this type here. I will also remove it. Okay? So how many components, how many connected components do I have now? This is one connected component. Here I have another one. Here I have another one. So I have three connected components. And Friedman defined that as the rank statistics. Okay? Sorry, that is the rank statistic. So here I have number of runs equal to 3. That means the number of edges that are connecting observations from different classes plus 1. Here I have to delete two edges like this, so I ended up with 3 connected components. The number of connected component is your round. Okay, let us look at the one-dimensional case. Suppose that here I have some observations from two different classes like this. Okay. Suppose that I have some one-dimensional observation and I have arranged them in increasing order. So I have to consider a complete graph on this many vertices, and after that I will construct the minimal spanning tree. What will be the minimal spanning tree here? So this will be the minimal spanning tree, isn't it? Because if you want to connect this observation to any other observation, these are the two nearest observations. Here the cost will be minimum. If you want to connect it here and then go back somewhere here, the cost will be higher. Right? I want a connected graph for which the cost is minimal, and naturally this is the connected graph. So in the one-dimensional case, minimal spanning tree is obtained by connecting the observation, by arranging the observation in increasing order and connecting them sequentially. And after that, to compute the rank statistics, what will you do? According to Friedman, I will delete this edge because it is an edge connecting one circle with a cross. So here I will be deleting this, here I will be deleting this. So the number of runs turns out to be 1, 2, 3, 4. Same as the usual rank statistics that we know in multi-dimension. Okay? So that is why it is known as multivariate rank test, and this was proposed by Friedman and Rowski. Okay. Is there any question regarding this? Yes.
I have a question. What is the cost about the construction of this minimal spanning tree in high dimension? Is it easy? Possible?
So dimensionality comes only once when you are calculating the distance. Once you have calculated the distances, after that the computational cost will remain the same. Okay. So it will be of the order d as far as dimensions. Linear. as I mentioned, it will give you the Wolfram-Fushan test for dimension 1. And there are several other tests that we will discuss. One of them is nearest neighbor. This is a much simpler concept. What I am doing here, I have some observations, x1, x2, xn from the first class, y1, y2, yn from the second class. So what does this sum indicate? I am looking at k neighbors of x, of course in terms of distance. Okay? K neighbors of x, and this is an indicator which gives you the value 1 when its rth neighbor comes from the same population. So basically, if you look at this sum up to, say, r running from 1 to k indicator of this one, it will give you the number of neighbors that are coming from the same population as xi. Okay? So here, basically it gives the number of neighbors out of the first k neighbors of xi which comes from the same population. And I am summing it over all such observation xi. And here I am doing the same thing. It gives you the number of neighbors out of k neighbors of yj which belong to the same population as yj. Okay? And I am summing it over all j, and this is the scaling factor. So basically this gives the proportion of neighbor that you get from your own population. Okay? If the two distributions f and g are all mixed up, so what do we expect? Almost half of the neighbor will come from my own population and half of the neighbor will come from g. So these statistics will take values close to half somewhere. But if the population is not well separated, what do we expect? All neighbors of x comes from this population itself, and all neighbors of g will come from that population itself. So if f and g are well separated, we do expect it to have higher values. So naturally we will reject the null hypothesis for higher values of this. So basically it counts the proportion of neighbors that comes from the same population. Okay? Yes?
How do you define neighbor in this case? Means
Which one?
in the NN test.
Sorry, I am not getting you.
How do you define the neighbors in the NN test case? Means it's a threshold of distances between
Neighbors?
Yeah.
So for any x, you can compute its distance from other observation.
Yeah. Means
So-
a threshold in range.
Oh, how do I choose the value of k? That I will come into that later. But given the value of k, it is clear. Suppose the value of k equal to 3 I need to use, or 4 I need to use. That is a prefix thing. How to choose the value of k, that is a different question, and I need to answer it in a different way. But for the time being, let me assume that k is known to me. So if k is 3, that means I will be considering only 3 neighbors. That means 3 closest observation, and I will check how many of them belong to the same population where I belong.
And the condition on neighbors, how you select the that particular point has neighbor this one. Means it's a distance based comparison or other thing.
It's distance.
Means how what distance? Means you
What distance at the time being I am considering the Euclidean distance.
No, I'm thinking about the measure of distance. Means it's 1 unit or 2 unit like that. How do you define the neighbors of a particular point?
Okay.
A particular node.
So suppose that I have some observations like x1 to xn, right, and y1 to yn. Now I am assuming that I can compute a distance between each pair of observations. It could be Euclidean distance, it could be something else. So for the time being, suppose that I want to find out the neighbor of x1. So what I will do, I will compute this distance x1 minus x2, x1 minus x3, and so on. And in this way, I can compute its distance from all other observations. So naturally, whom will you call a neighbor? The observation which has the smallest distance. So I will sort this, and on the top, the observations having minimum distance with xi will be called neighbor. If k equal to 3, I will be considering only 3 neighbors. If k equal to 5, I will be considering only 5 neighbors. Simple as that. Okay? So These are the two popular ground-based tests that we have in the literature. One is the multivariate run test proposed by Friedman, which is based on minimal spanning tree. Another one is the nearest neighbor test due to Schilling and Henge. This is much computationally much simpler as compared to the previous one. Okay. Not only ground-based tests, we have some tests based on average distances also. In a few slides ago, what we have seen that if the two distribution f and g differ, then the distribution of this guy, this one and this one differ. But here we have some stronger result. Under appropriate moment condition means the expectation has to exist. We have this result. This is an expected distance between one observation from the first class, is another observation from the second class. One observation from the first class, one observation from the second class. It is the expected distance between two observations from the first class. It is the expected distance between two observations from the second class. It says that this quantity is always non-negative. Okay? And equality holds if and only if the two distributions are identical. So, using this property, it is easy to construct a new test. What is that? I will just look for its empirical analog, which is given here. Okay? The expectation gets replaced by appropriate quantities. Sample version. So this is the test statistics we can look at. If f and g are equal, what do we expect? That its population version gets value very close to 0, so it is supposed to be very close to 0. If I have solutions. On the other hand, if f and g differ, then this is a positive quantity, so this is expected to be large. So we can reject the null hypothesis when the test statistics takes higher value. One can check that in one dimension this matches with the Kramer-Hormese statistics, and that is why it is known as the Kramer test. Okay, and there are several other tests based on distances that are available in the literature. One is based on it is an adjacency test based on non-bipartite matching due to Rosenbaum. There is a triangle test by Liu and Motorist. All are based on Euclidean distances. Okay. Now these are tests that we have in the literature. Now let us look at their behavior in the high dimensional setup. Because all these tests were proposed, say for instance Friedman. Friedman developed this test in 1979, this was in 1988 or 86. So 30, 40 years back, when we didn't bother about the high dimensional data. But these tests are based on Euclidean distances. Euclidean distance can be easily computed in any dimension, and so they have the potential application in high dimensional sample size setup. Okay. Similarly, this one also can be used very conveniently in the high dimensional low sample size situation. But now we need to study how they perform in high dimension. So here are two examples. Okay. So here f and g both are multivariate normal distribution. It's a simulated experiment. F is standard normal and g is mu1 means is a mean vector with all components mu. So this is the mean vector that I have considered, and dispersion matrix is sigma square times identity. So 20 observations were taken from F and 20 observations were taken from G. Okay? And based on this 40 observation, we tested whether the two distributions are identical or not. We have seen the test based on minimal spanning tree, that is due to Friedman and Rapsky. We have seen the nearest neighbor test. We have seen the Kramer test. Now we are studying the behavior of this test for different dimension, and the dimension increases along this scale. So note that in this problem, oops, in this problem, what about F? It is standard multivariate normal. So each component has normal 0, 1 distribution. What about G? It has a distribution like this. So each component has normal mu sigma squared distribution. And not only that, they are independent. Components are independent. So each of the distribution of each of the components differ in F and G. So as the dimension increases, what do we expect? We expect to get more and more evidence against the null hypothesis, because each of the variable contains an information against H now. Because the distribution of each variable is different in F and G, under F and G. So if I keep on adding the variable, we do expect to get more evidence against H now. And any meaningful test is expected to have power which converges to 1 as the dimension increases. So that is what we should expect in this situation, where each new variable gives you new information. So here evidence against the null hypothesis is getting stronger and stronger as the dimension increases. So we do expect the power to, we do expect the power to converge to 1 as the dimension increases. So here I have considered a location problem, where sigma square is 1, that means two populations F and G have the identical dispersion structure and they differ only in their means. In the case of location problem, we are getting what do we expect? What do we expect? In this case, the power of all three tests are increasing with the dimension. The Cramak test being the best, and the other two are also increasing. But in the scale problem, we have a different scenario. Scale problem means here I have taken the mean to be 0. So both populations have mean 0, and they differ only in the scale. In the scale problem, we have a different scenario. The Cramak test is not performing well, but still it is showing an increasing trend at the end. But what about the other two tests? It has power very close to 0. So they are not performing well in higher dimension. Cramak test is also not also fails to perform well, but is somewhat better than the other two. Whereas in the case of location problem, all tests are performing well, but in the in the case of scale problem, we have different scenario. And this is somewhat intriguing. So we need to study why this. Okay. Now, a little bit mathematical analysis will help us to answer the reason behind this diametrical opposite. So let us see what is happening. So in this set, I forget about this slide at this moment. Let us consider two observations, x1 and x2. This is coming from a normal distribution. And y1, y2, another two observations, independent of course, coming from that mu I, mu1. By that I mean this vector, mu, 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 mu. And here I am putting sigma square. So that was the setup in our experiment. Now what can we say about the distribution of this is going to be chi-square, right? Sum of square of some sum of squares of some normal. Not only that, this quantity I can look at it in this way, 1 by d sum over x1. Suppose this is the ith component of x1, this is the ith component of x2. So I can write down the square of the Euclidean distance in this way, right? I running from 1 to b. Now this is basically an average of IID random variable, because components are independent and for each I they have the same distribution. For different I they will have the same distribution, right? So this is an average of IID random variable. So if d increases, what will happen? It will converge to its expected value. Okay? Then you can use weak law or strong law, it will converge either in probability or almost surely. When will it converge? To its expected value. Expectation of this one. Oh, sorry, it's a IID. So it will converge to its expected value and the expectation of one of the thing. X1 1 minus X2 1. So converge here. And you can check that in this case it will be 2 times sigma square. Or 2 times sigma square is 1. Sorry. In the first case it will be 2. Similarly, so what we have seen that this quantity x1 minus x2, this will converge in probability or almost surely whatever it be, it will converge to 2. Similarly, using the same analogy, what we can show that this will converge to 2 times sigma square. And we can also show that this one, the same thing, it will converge to say sigma square plus mu square plus 1. Here is the variance of the second component, variance of the first distribution, and here is the difference between the two means. Because instead of chi-square, here you will have non-central chi-square distribution, and believe me, this will be the parent. So what is happening in the location problem is like this. In the case of location problem, let me go back to the previous slide. Location problem. So we had mu equal to 0.3, sigma equal to 1. So this quantity was 2, this quantity was 2 again, and this quantity was 1 plus 1, 2, 2.3. So after some scaling, the square of the Euclidean distance of the first type, that means when we have two observations from F, converges to this. When we have 2 observations from G, after some appropriate scaling, it converges to that. And we have 1 observation from F and 1 observation from G, after appropriate scaling, it converges to that. So what do we expect? That this type of distances are much bigger as compared to this two. Okay? So what happens to the nearest neighbor statistic? All x's, take any x1. What can you say about its neighbor? We need to compute its distance from other observation. Now, distance from the x observations are much smaller as compared to the distance between distance from the y observation. So x will have all its neighbors from the same population. What happens to the neighbors of y? Again, because of the same reason, y will have all neighbors from its own population. Isn't it? So as a result, the nearest neighbor test statistics will take its highest value, that is close to 1. What was the nearest neighbor test statistic? The proportion of observation that we are getting from the same population. And that is what is happening. X is having all neighbors from its own population. Y is having all neighbors from its own population. So the test statistic takes highest value. So naturally the nearest neighbor test will perform well. Okay. What about the Friedman-Rapsky statistic? Friedman-Rapsky to understand what will happen to the Friedman-Webster statistics, we need to know something about the algorithm for constructing minimal spanning tree. So let me tell you how to construct the minimal spanning tree, and then things will become easier for us. So here we have several vertices. And what was Friedman-Webster's test? We considered a complete graph on these vertices, right? And not only simple graph, it was an edge-weighted graph where each edge has a weight. What was the weight? Same as the Euclidean distance. Okay. So consider a complete graph on these vertices, an edge-weighted complete graph, where each edge has a weight associated with it or cost associated with it. How to construct the minimal spanning tree? There are two different algorithms, or popular algorithms. So one is due to Prim's algorithm, another is Kruskal's algorithm. So one can use either of the two, and most of the cases, or except for some pathological cases, they will lead to the same result. And so when the minimal spanning tree is unique, they will give you the same thing. Okay. It goes in this way. Let me describe Prim's algorithm. It goes in this way. First, I will connect the two edges, two vertices, which has a minimum distance between them. So I have n choose two pairwise, or capital N choose two pairwise distances, and among them I am choosing the edge having the smallest weight. Okay? So that I have chosen this. Now I am dividing the whole set of vertices into two parts. One that we have containing these two only, and the rest. Now I will be looking for an edge which will start from here and end outside. So how many such choices are there? If there are n many vertices, then I have two vertices over here and n minus 2 vertices in the other set. So there are 2 into n minus 2 such choices. Right? I can start from here, go anywhere. So these are the choices that we have. Among these 2 into n minus 2 such choices, I will be choosing the one which has the minimum value. So suppose that this is the minimum value, I am choosing it. Okay, so next time, this is one set and the remaining is the other set. I will be looking for an edge which will start from one of these three edges and end up somewhere. So suppose this is the case. Okay, so next time I will have 4 edges in one set and the other set containing them. So suppose these are the things that we have, and in this way I can construct the minimal spanning tree. Okay, so this is one way of constructing the minimal spanning tree. Now what will happen in the case of location problem? If I use this algorithm, what is happening out here? The distance between two x observations and two y observations are almost the same, and they are much smaller than the xy distance. So naturally, at the first stage, either two x observations will be joined or two y observations will be joined. We do not expect to join one x observation with one y observation. Right? So suppose x and x, two x observations, say xi and xj is joined. The next time, I have the remaining observations out here, but I am looking for an edge from here to outside. So naturally, from here I am looking, if I look at the distance of all other observations, naturally at x observation I will get as the smallest. So this will get connected with an x observation. Here also, if I start with from there, then also I do expect to get an x observation. Right? In this way, I will exhaust all x observation first, if I start from x. Okay? And after that, the y observation will come, and once I get an y observation, this will be connected to other y observations, like this. Okay? So my minimal spanning tree will be like this. All all x observation will be nested in one part, all of y observation will be connected in another part, and there will be only one edge connecting x and y, because that is the costly edge. So if we remove this one, I will get the run statistics. There is a number of connected components, and that will turn out to be 2. So we do expect that in the higher dimension, in this setup, the minimal, the test statistic, the Friedman-Dubsky test statistics, or TMST, will converge to 2 in probability. And that is the smallest possible value of the test statistics. So naturally, the null hypothesis, it is a stronger evidence against the null hypothesis. It is taking the minimum possible value. So the null hypothesis will get rejected. And that is what is happening out here. Okay? So we are getting all neighbors from our own population, and because of that, the nearest neighbor test is performing well. If I look at the Friedman-Dubsky statistic and construct the minimal spanning tree, I will get a construction like this, or the minimal spanning tree structure will be like this, and as a result, the test statistic will take its minimum possible value, that is 2, and as a result, the null hypothesis will get rejected. And that is what we expect, right? In higher dimension, because here, in this particular setup, we are getting more and more information against H naught as the dimension increases. But something strange is happening out there in this case. What is happening out there now? Just look at the value here. It will still remain 2. What about this one? Sigma square is 1.3. So this will be 2.6. What about this? Is sigma square plus mu square plus 1 will be 2.3. Now the ordering gets changed. Now xx distance at the smallest, then comes xy distance, and then comes yy distance. Okay, so this is here. So if I look at the neighbor of any x observation, I do expect to get neighbor from the x observation itself. But if I try to find the neighbor of y observation, what will happen? I do not expect to get neighbors from y observation, because the y distances are much bigger compared to xy distances. So neighbors of x will come from the first class. Not only that, unlike the previous case, neighbors of y will also come from the first class. Isn't it? Y distances are much bigger compared to xy distance. So for any y, your x observations are much closer compared to the other y observations. So as a result, if I look at the proportion, if I look at the this test statistics, whatever I'm saying, what was that? Here, these indicators, all these indicators will be 1, because x neighbors will come from neighbors of x will come from the x population itself. But what about neighbors of y? They will also come from the x population, not the same population where y belongs. So all these indicators will be 0, and all these indicators will be 1. As a result, the test statistics will take some values close to half if the sample sizes are balanced. And as a result, the null hypothesis, and that is the expected value of the test statistics under, or close to the expected value of the test statistics under H naught. So the nearest neighbor test will not be able to reject the null hypothesis. And that is what is happening out here, and because of that, the nearest neighbor test, the power of the nearest neighbor test is close to 0. Okay. What about Friedman and Dubsky? Well, let us try to construct the minimal spanning tree again in this setup. What do we expect? Now these are the xx observations are the smallest. So the first edge that I will get is between two x observations. Okay? Say x1 and x2. These are the two observations, I got the smallest. Now next, I will be looking for an edge from here to outside. So from here, I can get xx distance or xy distance. Now xy distances are much higher compared to xx distances because I have this order. So xy distances are much higher compared to xx distance. So what do I expect? This will connect to another x observation. And in this way, all x observations will get exhausted. Right? And after that, the y observation will come one by one. So like before, up to this, the same as before. Now I am getting a y observation here. In the previous case, once I get a y observation, I was supposed to get edges from there. Now what will happen? Now I am looking for an edge from this side to outside. What we have outside this set are all y observations. So they will get connected to this one. Now a new y observation can get connected with this one or can get connected with this x. Now which one is more likely? Naturally, this xy distance is much smaller compared to yy distance, so it will not go for this one. So I will have an edge like this. Okay? So all the rest of the observations are likely to be connected with one of the x observation there. And my minimal spanning tree will look like this. So when I will remove the edges between x and y observations, what do I expect? These edges will get removed. I do expect to get one connected component containing all x observation. And what about the other connected components are singleton y observations. Right? And as a result, the test statistics will take how many values? The sample size for y, that is n plus 1. Plus 1 for the x observation. Okay? So much higher than 2 that we had before. And here, in the case of Friedman-Debski statistic, we reject the null hypothesis when the number of run is small. But it is not small, and so nearest neighbor Friedman-Debski test failed to reject the null hypothesis. And that is what we observed here. The power of the Friedman-Debski test went down as a dimension. What happens to the Cramer test? Okay, for that we need to go to the next slide. So the phenomena that I said, it's not only for normal distribution. Okay, I started with the normal distribution to demonstrate it, but this phenomena you can observe for any other distribution. Here the results are written over there. You have two IID observations from a distribution. The distribution is not specified over here with the mean vector mu f and the dispersion matrix sigma f. We have two observations from another distribution with mean vector and dispersion matrix. Now I am assuming this that the norm of the difference between the mean when divided by 10 to the power minus 1 goes to some quantities like this. These if I divide with the trace by d, I'll get this. This is basically the average variance of the first component. Here we have the average variance for the second component, and here we have another term. In our case, this was mu square, this was 1, and this was 1.3 or sigma square. It says that this type of convergence will hold under some appropriate assumptions. What are the assumptions? We need to get uniformly bounded fault moments and weak dependence on the measurement. So normality is not needed, even IID setup is not needed. Okay? It generally holds, and there also we will have the same scenario that in the case of scale problem, this test will not perform well, whereas in the case of location problem, they are expected to perform well. Okay. Now, let us go back to the to a case. What happens in the case of Cramat test. Okay. Oh. So let us write it down, the result that I will be using. So if x1 and x2 are coming from a distribution with mean vector mu f and dispersion matrix sigma f, and y1 and y2 are two ideal observations from another distribution with mean vector mu g and dispersion matrix sigma g, then I know under some assumption the convergence of the pairwise distances. This converges to 2 sigma f square. Sigma f square, what is that? Sigma f square is basically, okay, let me write it down at that. y1 minus y2, 2 sigma g square, and here I have sigma f square plus sigma g square plus mu square, where the definition goes in this way, mu square, right? Mu square. The mu square is the limiting value of the trace, and the limiting value of this one. Sigma 1 square is the limiting value of the trace of sigma 1. And sigma 2 square is the limiting value of 1/d times sigma 2. That means variance of all the component and dividing by it. This is something like average variance, and this is also like average variance. And the previous one is the average deviation in terms of average deviation, the square deviations between the mean vectors. Okay, so this quantity, I am denoting it by DFF. That means the limiting value of the distance between two populations from F population. Limiting in the distance means the scale distance I am talking about this. This is I am calling BGG, and this is I am calling DFG. Now if you look at the Cramer statistics, what was it? Cramer statistic has the definition. What's this definition? So naturally, where did it converge after appropriate scaling? This will converge to its limiting value. This one will converge to its limiting value, and this one will converge to its limiting value. What will be the limiting value after some appropriate scaling? This will be this distance between x and y. So basically DFG. This will converge to the distance between two x observations. So basically DFF, and this will converge to the distance between two observations from G. So basically DGG. So after appropriate scaling, what do they expect? That it's not correct, but this Cramer statistics divided by D should be there. Will converge to this. Now I can break it into two parts like this. DFG minus DFF and DFG minus, the next one will be DGG here. So DFG minus DFF plus DFG minus it should be DGG. Now in the case of location problem, what we have seen that xy distances are much bigger compared to the xx distances and yy distances. So in that case, we do expect to have DFG much higher than DFF and DGG. So both quantities are positive there. But in the case of scale problem, DFG, that is this distance between x and y observation, lies between these two. So one of them has positive sign, the other of them has negative sign. And as a result, there some cancellation was going on, and as a result, the value of the test statistics was not that high. And as a result, the power dropped down. Because we are rejecting the null hypothesis for higher values of the test statistics. When DFG dominates these two, then we have a positive term here, and then add it up and give you a higher value. But in the other case, the scale problem, your xy distance lies between x and yy distance. So in that case, we have some positive term here, but so these two terms are of different sign. As a result, the cancellation goes on, and we may have some value close to 0, which leads to the acceptance of the null hypothesis, and that is why we had lower power here. And for the nearest neighbor test, I have already described the phenomena, so I am skipping it. For the test based on minimal spanning tree, I have also described it. So let me see. So what we have seen, that if this limiting value, that means the distance between x and y observation, dominates DFF and DGG, that means the limiting value of x-x distances and y-y distances, then we do not have any problem. But if this one lies somewhere between these two, then we have some problem. Note that this cannot be smaller than both of them, because Friedman and Rapsky's because of this Body-Hahn-Span's result, from there what we have is DFG minus DFF minus DGG. This will be always non-negative. So this one cannot be smaller than both of them, but it can be smaller than one of them or bigger than both of them. If it is bigger than both of them, we do not have any problem with this test. But if DFG, that means the limiting value of the distance between x and y observation, is smaller than one of the distance, xx or yy distance, then we have some problem. So how to take care of it? Okay, some simple solutions are here. We have seen that the Cramer test statistics can be written in this way. As d tends to infinity, this gives you DFG minus DFF, and this gives you DFG minus, this should be DGG again. Okay. So we have seen the cancellation of these two terms, means one of them is positive and one of them is negative. That was creating the problem. How to take care of it? A simple thing, take the square of these two, and came up with the statistic. Okay. So if we do that, the test statistics will look like this. This Cramer test statistics, square, and plus something like this. This added term, what is that? This is the distance between x and x observation, and this is the distance between g and g observation, and y observation and xy observation. Now, if they have different scales, then they are supposed to differ, and as a result, it will have some contribution. So, this contribution will come only when f and g distributions differ in the scales. And if they differ in the scales, then if I have larger scale, then distances are supposed to be larger. Right? So this difference, or if there is a scale difference, this gives you a significant contribution to the test statistics, and as a result, the test may perform well. What about other thing? Nearest neighbor test statistics was like this part plus this part. Now I am saying this is equivalent to using these statistics because I have subtracted some constant term. The constant term are not supposed to create any disturbance, right? What I was doing was rejecting the null hypothesis when this term plus this term is large. So what I can say that is equivalent to reject the null hypothesis when this term plus this term is large. Because what I have subtracted is a function of sample observation, a function of the sample sizes only. It is not functions of xi. So basically constant. So equivalent to use this one. Now look at this. This is basically the expected value of this guy under h naught. And this is the expected value of this under h naught. Okay? Now something similar to this phenomena happens here in the case of scale problem. We have noticed that in the case of scale problem, this IRX, these indicators were taking the values 1. Because X observations were supposed to get neighbors from its own population, so all indicators were 1. So this was taking much higher value. Whereas here, again typo, here should be Y. It should be N and this should be Y. Again, for the Y observation, these indicators were all 0. Because none of the Y observation had neighbors from its own population. So this quantity was negative. So here we had some positive quantity because this takes much higher value compared to its mean. Here I have values close to 0. When we subtract the mean, it is going to be a negative quantity. So when we add them up, again some cancellation takes place and as a result nearest neighbor goes down. We can interpret it in this way. So how to take care of it? So instead of just taking the difference, take the mod of the distance or the square of thing to get rid of that. Okay, and that test I am calling it modified nearest neighbor test. Just this simple modification. Here also it is a simple modification. Now how to modify the Friedman-Napski test? Okay, so let me first look at the result, this modification, and then I'll come back to this. So here some proposal for the modification of Friedman-Napski test. I'll come into that later. But let's see how this modification, whether this modification works or not. In the case of location problem, so these three solid curve we had before. Now we have some dotted curve for the modified test. But we can see that in the case of location problem, they are performing well, but not as good as the original test. But in the scale problem, in the case of scale problem, where this we have given a safeguard against those cancellation of positive and negative terms, nearest neighbor and nearest neighbor test and the Cramer test both are working well as compared to the original test, which had power like this. So this modification, simple modification works. Not only that, we have proposed a modification for the Friedman-Napski test also. And what is that modification? I haven't described it. But what we can see that modification is also working. Not in the case of location problem, it has almost the same power as the Friedman-Napski test. But in the scale problem, location problem, it has almost the same power as the Friedman-Napski test. But in the case of scale problem, it is performing way better. Which one is? This one, SHP, is performing way better than the Friedman-Napski test. So this some small modifications we have done, and these modifications are working well. Now let me come back to this Friedman-Napski test. We have already seen what is the problem in the test involving minimal spanning tree. And now I'm describing how to take care. So here our methodology remains same. So again we consider the pooled sample consisting of n plus n observations. And again we are considering a complete graph, age-weighted complete graph, where the age weights are defined using Euclidean distance. In the Friedman-Napski test, what we did, we constructed the minimal spanning tree. So here I am not constructing the minimal spanning tree, but going for another graph, and that is known as shortest Hamiltonian path. What is shortest Hamiltonian path? Here I am not looking for a tree, but a path. Okay. Earlier, if I nodes like this. So I was looking for a structure like this. Structure like this. Now I am not looking for a structure like this, I am looking for a path. So I will not have a road network like this. But instead of that, you can start from somewhere like this. You may go here, 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 here. Like this. I am looking for a path. And once I have the path, it's easy to define the run statistic. Because I can stretch this path to make a straight line. So that is just like the univariate case, and we know how to calculate the run statistic there. Because on the path I will get some crosses and some circles, and I know if I stretch it, how to compute the run statistic. Right? So here, for the shortest Hamiltonian, so this is called Hamiltonian path. Starting from where? Starting from one vertex, I am visiting each vertex only once, and no path is being repeated. I want a graph like this. But once you can say here also several paths are there. So basically, finding a path means a particular arrangement of 1 to capital N. Right? The number of paths is equivalent to the number of permutations that we have here. Because this permutation 1, 2 to n means I'll start from the first vertex, visit the second one, visit the third one, and so on, visit the n one. Similarly, here if you have I1, I2, In, that means I'll start from the I1th vertex, visit the I2, then I3, In, and so on. So there are n factorial many choices, and out of this n associated with each of these n factorial arrangements, I will have a cost. What is the cost? The cost of the paths, sum of the cost of the paths, sum of the cost of the edges. That is the cost of the path. And naturally, one will look for the path for which the cost is minimum. And that is what is called the shortest Hamiltonian path. Okay? So instead of spanning tree, they did some simple modification is that instead of minimal spanning tree, they look at the shortest Hamiltonian path. And once I have the shortest Hamiltonian path, I know how to compute the run statistic. This is exactly the same that we do in the univariate case, and that was the run statistics they proposed. Now, I can't prove the result at this moment, but the result is like this. Okay, let me do one other thing. That what happens in the univariate case? What is the shortest Hamiltonian path in the univariate case? So, suppose that I have these observations in the univariate case, the shortest Hamiltonian path will be naturally like this. Right? Join the observation in increasing order or decreasing order. So, one-dimensional case, shortest Hamiltonian path and minimal spanning tree are set. Okay? And that will lead to the same test, that is the usual run test. Because here also, I will do the same thing. After finding the path, just remove this one to get your run statistic. So in one dimension, whether you use the shortest Hamiltonian path or you use the minimal spanning tree, the resulting statistic that you get out of there is the run statistic, so 150 times statistic. So this can be viewed another generalization of the univariate run test for the multidimensional problem. So what is the advantage of using what is the disadvantage of using shortest Hamiltonian path? The disadvantage is that unlike minimal spanning tree, here we do not have any exact algorithm. Like Kruskal's algorithm, Prim's algorithm, we do not have an exact algorithm. So one has to use a heuristic algorithm for that. So that is one problem. So computational problem is there. So one has to depend on a heuristic algorithm to find out the shortest Hamiltonian path. It may not be the optimal one. You may get the suboptimal solution. But the minimal spanning tree, there are algorithms like Kruskal's algorithm or Prim's algorithm, which I have described for finding out the minimal spanning tree. But unfortunately, we do not have any such algorithm for the shortest Hamiltonian path. There is one drawback. But there is a theoretical advantage. What is that? The advantage is given up there. These two red lines will tell you the story. If mu square is bigger than sigma 1 square minus sigma 2 square, difference of these two. That means the location difference dominates the scale difference between the two populations. When this thing happens, then we have seen that the minimal spanning tree, the test statistics based on minimal spanning tree converges to 2. Because we have one connected component consisting of all x observation and one connected component consisting of y observation. So basically, here, if you look at, if you recall the limiting value of the distances, now what it says that mu square bigger than sigma 1 square minus sigma 2 square, it means that DFG, the distance between x and y observation, is bigger than DFF and DGG both. That is an ideal situation. But if mu square is less than sigma 1 square minus sigma 2 square, what happens? This DFG lies between these two. So this is just like the location problem, and this one is just like the scale problem that we discussed before. So when this thing happens, then the distance between x and y observation dominate xx and yy distances. So that is an ideal situation because the neighbors of one class are coming from that class, because I have the neighbor from my own locality. So here also there is an ideal situation, and in that situation, the test based on minimal spanning tree, we have seen that the test statistic converges to 2. What we can show, the test based on the shortest Hamiltonian path also converges to 2. So both are taking minimum value and they are equally efficient. But when this thing happens, is the location difference gets dominated by the scale difference, then then we have a situation like this. This DFG lies between these two. So we know the neighborhood structure gets violated because y do not have neighbors from y population anymore. And then when the neighborhood structure gets violated in higher dimension, we do have some strange problem. While we have seen that the minimal spanning tree, the rank test, the test statistics based on minimal spanning tree converges to n plus 1 or n plus 1, depending on which one has smaller scale. But in that case, what we can show that the shortest Hamiltonian, the rank statistics based on shortest Hamiltonian path converges to 3. It means if you look at the path, then probably this will be the structure. I cannot give you the proof at this moment, but this will be the structure. Suppose that F has smaller variance than G. Then what will happen? We will start with G observations. In between, we will have a sequence of all F observation, and then we will end up with G observation. This will be the ideal sequence for which the cost will be minimum. And as a result, the test statistic will take the value 3, which is very small, and it will reject the null hypothesis. And that is why it is performing well in the case of scale problem, where the minimal spanning tree, the test statistic based on minimal spanning tree could be performed well. So this is the moral of the story. We do have some theoretical results, and the first theorem states that if mu square bigger than 0 or sigma 1 square not equal to sigma 2 square, that means whether if there is a difference in the location or in the difference in the scale, then the power of this modified test, BG means the modified version of Cramat test, MN means the modified nearest neighbor, and SHP the based on the shortest Hamiltonian path. You can show that under appropriate assumption, the power converges to 1 as the dimension increases. Cramat test also has this property, so it has a high dimensional consistency, but as I have mentioned, in the case of scale problem, because of the cancellation of positive and negative terms, it often has low power, especially in the case of when the sample size is small. Okay. If mu square exceeds this, that means the location difference dominates the scale difference, then we do not have any problem with the nearest neighbor test and minimal spanning tree. But if it is other way around, and the location difference gets dominated by the difference scale difference, then we have seen that the nearest neighbor test and the minimal spanning tree, the test based on minimal spanning tree may not perform well. So there is a theoretical result which states that the power may even converge to 0 as the dimension increases, depending on M and N. Means condition on M and N means one of them is not too large compared to the other one or something. Now, so far I know that if there is a location difference or scale difference means note that sigma square is the average variance. Sigma 2 square is the average variance for the second population, and sigma 1 square is the average variance for the third population. So it says that if there is a difference in location or difference in average scale, then one of these 4 tests, BG, MN, this one, or the Cramat test, they have the high dimensional consistency, but we do not have the high dimensional consistency for the nearest neighbor and MST RAM test. We do have this consistency only under some special situation. In this situation, they have the consistency. In this situation, they do have some problem. But we do not know what happens when there is no location difference and the average variance are also same. So the next question now comes, what happens to this test when the two populations at the same location and same average variance? So here are 2 examples. Note that the first population is normal, so the second population is also normal. They have the same location, that is the origin, and they have different dispersion structure. So see, this is lambda 1, this is lambda 2. Lambda 1 is a diagonal, where the first d by 2 elements are 1 and the next d by 2 elements are 2. Here we have the just opposite scenario. The first d by 2 elements are 2 and the next d by 2 elements are 1. So in these 2 populations, they do not have any difference in location, so mu square is going to be 0. They do have different variance structure, because the first component here follows normal 0, 1 distribution, whereas here it follows normal 0, 2 distribution. Similarly, here the last component here follows normal 0, 2, here normal 0, 1. So each of the variable has different distribution here in F and G. But if you look at the average variance, the average turns out to be the same. So what happens in this case? Let me start with the test based on average distances. There is a Cramat test and its modified version, which is known as the BG test. You see that they have no power. Okay. So here is another example where F is a multivariate distribution whose components are independent, and each independent and identically distributed, normal 0, 5. And G is another population which also has independent component variables, or maybe independent and identically distributed component variables, and each component follows a T distribution, 5 degrees of freedom, and the scale parameter is 3. The scale parameter is chosen in such a way that the variance of this distribution matches with this one. Okay, variance of this distribution matches with this one. So basically here in these 2 populations there is no difference in location, no difference in scale. And unfortunately both of them, in this Cramat test or this modified version, they are not performing well. So whenever, so these 2 examples shows that here we do not have have a difference in location, but we did have some difference in the dispersion structure. But as because the average variances were same in these two populations, the Cramer test and the BG test based on Euclidean distance couldn't perform well. Here also we have some scenario, but here they have the same mean and the same dispersion structure, they differ only in their shape. But neither the Cramer test nor the BG test could detect it out. So the next session probably we'll try to find a solution.